All right, so we'll continue. This is part 2 of the answers video for the winter packet, and we'll continue with number 14. So define the octet rule. The octet rule states that atoms want to fill their valence orbital. That's just that simple. Now for hydrogen and helium, the first orbital can hold 2 electrons, so that would be 2 electrons. For everything below, it would be 8 electrons to fill a standard octet. So that would do that. Now for extended octets, any element from the 3rd row down can have up to 12 valence electrons. That's called an extended or an expanded octet. So the standard octet would work like this. So we can have an oxygen, and it can be bonded to hydrogens. So the oxygen, before it's bonded, let's draw that, is going to have 6 valence electrons. So it has 2 docking stations, if you want to think of them, for hydrogens. One there, and I drew it on this side, but it could on either side. It doesn't matter which side you put it on. And hydrogen has 1 valence electron, so it has 1 location where it can have a second electron. Okay, for oxygen there's 2. All right, so if they join up, since 2 hydrogens join up with an oxygen, the oxygen has an octet 1, 2, 3, 4, 5, 6, 7, 8, and each hydrogen has an octet 1, 2 because that's all it can hold. If we're looking at an ionic bond, you have an Na, and it has a single valence electron, and then you have a Cl, which is a nonmetal. This is a metal. This is a nonmetal. The nonmetals are the strong guys. And it has 7 valence electrons according to your periodic table. So what can happen is this electron, which is on a low ionization energy metal, which means it easily loses electrons, will jump over here to the chlorine right there. Once it does that, the chlorine becomes a negative charge, and the sodium, and I'll just erase the electron now. So that electron jumped over here, and the sodium now has 1 less electron than protons, and so it's going to be a plus charge. And the plus and the minus attract each other. Okay, so once sodium has lost that electron, it loses the electron in the 3rd orbital, so it now goes back and now has the electron configuration of neon. So if you were to draw its Lewis dot structure, it would have a full octet, but it would also have a plus sign there. Okay, typically you put brackets around it. You can do that or not do that. Okay, and chlorine, of course, has what we just showed. It has a full octet because it picked up an electron. Chlorine picked up an electron to be like argon, and everybody wants to be like a noble gas. And then you'd put a minus sign there. They attract each other. All right, so that is the octet rule. Number 15, atoms want to have the same blank as the nearest noble gas. This means that the element is blank to the noble gas. The word is 2 words here, electron configuration. So I'm just going to say it, you write it. So atoms want to have the same electron configuration as the nearest noble gas. This means that the element is isoelectronic to the noble gas. So isoelectronic is isoelectronic. All right, so that would be the answer to number 15. So you write it, I'll say it, you write it. Okay, for number 16, it says describe an ionic bond based on the following video at minute 8. So there's the link to the video. If you go online to the Canvas site for the winter program, there it is. Or if you go to the regular website, and I'm not sure whether you have access to that now, that's why I'm doing it this way. It's day 13. It's day 13 ionic bonds, and it's found at minute number 8. And just not only copy that, but memorize it. You need to learn this definition cleanly going into the 2nd semester. Okay, so I'll show you that website. And there it is. This is what I want you to be copying right there. All right, so go to that website and watch that and copy that down. All right, let's keep going. What two names are given to the smallest unit of an ionic bond? So I'm going to state those. It's called a unit cell, UNIT-CELL, or a formula, FORMULA, unit, UNT. It is not an independent structure. I want you to write that down. It's like bricks in a wall. So the image I often draw is sodium chloride. So you got NaCl, NaCl. So there's no such thing as an NaCl molecule, an independent structure called an NaCl molecule. So I'm going to cross that out. No such thing. There is a formula unit. It means the lowest ratio of NAs to Cls in this ionic bond is 1:1. So therefore its formula unit, or the unit cell, is NaCl. Okay, so that's the answer to that, and you can draw this. Always write what I write, and write what I say as well. So I gave you the definition. Okay. 18. Are these structures mobile or fixed in one location? So they're fixed in one location. So unit cells or formula units are fixed. They're like bricks in a wall of a salt crystal, or like apartments in an apartment building. You can tell one from the next, but they cannot move around independently. And if you do break this up, you break it up through an ion-dipole interaction, in which the positive side of a water molecule, the hydrogen side, will pull away the chlorines, and the negative side, the oxygen side, will pull away the sodiums. So I want you to write that down as well. If you don't write down these things, you're not going to get credit for the assignment, okay? I'm not writing them down because I don't want this to be a copying exercise. I want you to think about what I'm saying. If you need to go back, just turn the video back a minute or two and listen to it again, okay? All right, number 19. What name is given to the entire structure of an ionic bond? And that is called a crystal, C-R-Y-S-T-A-L, crystal lattice, L-A-T-T-I-C-E, structure, a crystal lattice structure. So that's the whole apartment building. The formula units are the individual apartments, and the crystal lattice structure is the entire apartment building. All right, now crystal lattice structure, those sodiums and chlorines are held together by an energy called lattice energy, L-A-T-T-I-C-E, energy. So I want you to write that down as well, okay? So the ions in an ionic bond are held together by a lattice energy. All right, what name is given to the entire structure of an ionic bond? And that is a crystal lattice structure. Okay, so number 18, they are fixed in one location, and they are in the structure that I mentioned called a crystal lattice structure. Okay, if you write it twice, that's okay. It's all the better. Number 20, the energy that holds an ionic structure together has what name? And that's called lattice energy. So what's holding the Na to the Cl, and remember, it's not being held to one Cl, it's being held to Cls on all sides of it, all four sides, and then front and back as well. So 6 different sides. That sodium is being held to a chlorine, and the same is true of a chlorine. It's being held to sodiums on 6 different sides. Okay, and that energy is called lattice energy. All right, we now move on to page 6, question 21. It says, describe a covalent and polar covalent bond based on the following videos. And this comes from day 14, covalent bonds. Okay, and I want you to answer the next 3 questions from that. What structures do covalent bonds form? And are these structures mobile, or are they stuck in fixed locations? Okay, so I want you to watch that. So I have the minutes here. So from minute 133 to 511 gives you basic definition of a covalent bond. 640 through 950 talks specifically about polar covalent bonds. So I want you to be able to describe those cleanly. So it comes from right here. Right there, it's day 14, and there's the video. Don't have to watch the whole video, just be able to answer the question about covalent and polar covalent bonds. Okay, there it is. So what structures do covalent bonds form? I'll tell you that right now. They form molecules. Molecules are independent structures. And are these structures mobile or stuck in fixed locations? They are mobile. Okay? So if you have 2 water molecules, look like Mickey Mouse. And if you boil the water, one of them can float off in this direction and one of them can float off in that direction. They are independent structures, unlike formula units or unit cells. All right, let's keep going then. So go ahead and just stop. Go to that video and give the definition of a covalent bond, polar covalent bond. All right, the next two problems, 24 and 25, I'm going to do completely with you. It's critical that you know how to do these problems well, both for the tests in my class, but more importantly for the AP exam. They're going to ask you these two types of questions. This first one is, how many grams of CO2 can be produced from 5.82 grams of C2H4 and 8.9 grams of O2? All right, so this is a limiting reactor. I want you to write that down. Anything I write down, you write down. You'll have to learn to quickly classify a problem, and many times once you can do that, then the type of solution that you need or the way you need to approach the problem jumps right to mind. Okay, so this is a limiting reactant problem, and the way we did that is we performed the reaction twice, at least in theory. You combust all the C2H4 and you see how much O2 is required to do that. Next, you do a reaction where you combust all the O2 and you see how much C2H4 you need to do that. All right, so the first thing you're going to do on this problem, I've given you the molar masses. Okay, let's be sure you know how to compute those, and this should be like saying your own name at this point. But you have carbon, you have 2 of those, times 12.01, which equals, so 24.02, 4.04, when you add those together, you get 28.06. So be sure you know how to do molar masses. And some of them you should kind of eventually get memorized just by using them enough. Oxygen, O2, is 32, CO2 is 44.01, and water is 18.02. Okay, so now we need to do a molar mass conversion. That should not be a mystery to you at this point, how we do this, okay? Practice them. Okay, so at some point you've got to grind this stuff into your memory, okay? We've done enough of these, you should be able to do that. Okay, so let's go ahead and do it for C2H4. So it says that we were given 5.82 grams of C2H4, and the molar mass is 1 mole of C2H4 equals 28.06 grams. We need moles on the top because we're converting to moles. Okay, now again, the shortcut way to do this is instead of writing this equivalency as a conversion factor, just put the 28.06 down underneath the 5.82 and do the division. You can just do it that way. Okay, so you end up with 0.21 moles of C2H4. Now for the oxygen, I'm going to use the shortcut way. Okay, so we're starting with 8.9 grams of O2. And that gives us 0.28, and that's moles of O2. So you see this method takes a lot less space than this one. You don't have to do the formal stoichiometry all the time. Okay, so now we're going to go ahead. We know we have, circle that number and circle this number. We know we have this much C2H4. That's exactly how much we have. We know we have this much O2. That's exactly how much we have. All right, so in the all C2H4 under C2H4, this box right here, we're going to put the amount of C2H4 we were given in moles. Again, it's got to be to moles. Chemical equations don't understand grams. They don't know anything about it. Everything up here is in moles now. Okay, now for the oxygen, we have 0.28 moles of O2, so you go to the all O2. We're going to combust all of that, and it's underneath O2, so it goes in this box right here. On the AP exam, they're not going to give you all this space to draw boxes, but I will show you how on a multiple choice question, if you know how to use your space properly, you can do this. Okay, so now we have to look at how much O2 would we need to combust all of this. We want to combust all of this. How much O2 do we need? Well, we look up at this relationship. We need 3 times as much O2 as the amount of C2H4 we want to combust. In other words, you need 3 moles for every 1 mole. So if we want to combust 0.21 moles of C2H4, we need 3 times that many moles of O2. Okay, so I'm going to go ahead and 3 times 0.21 is 0.63. Use a calculator if you can't do that in your head. Don't worry about it. Okay, so now we're going to combust all of the O2, and we have 0.28 moles of O2. So what we're going to do is we're going to divide this by 3, and what you'll get is 0.0. And I'm going to go one more significant figure here. Well, it's not more significant figures, so I'm going to keep it the same number of significant figures, 1 digit past the decimal. So again, what is this saying? It's saying we need 3, in order to combust all the C2H4, we need 3 times as much O2. So to combust all the C2H4, we need that much O2. That's 3 times as much. Now, if we want to combust all the O2, we need 1/3 as much. For every 3 moles of this, we need 1 mole of this. So we divide this by 3. So the way to check your work here is simply to say, this number is 3 times this number is 3 times this number, and this number is 3 times that number. Okay, so we now have our reactant set up. So now what we're going to do is we're going to go around and we are going to say yes, yes, no, and I had a Y written there already, and I should have a Y written down here. Yes, we know we're asking the question, do we have at least this much C2H4, and do we have at least this much of each of these reactants? So yes, we have at least this much. We have exactly this much because that's the number we have here. And we have at least this much O2 because that's the number we calculated here. So those are both automatic yeses, those 2 boxes. Now we go around and say, okay, if we want to combust this much C2H4, do we have this much O2? And the answer is no. We only have this much O2. Or the simpler way to look is just look down here. This is how much we have. We don't have 0.63. So that's going to be a no. Okay, now we come down here, and you're only going to have 1 no, so you could quit right now, but let's just check this one. So to combust all of the O2, we need this much C2H4. Do we have this much? Yes, we have much more. We have that much C2H4. That number is bigger than that number. So yes, that's a yes. You should always end up with 3 yeses and a no. And so now we know that the limiting reactant is the one with the no in the column. So I'm going to put that up here at top. This one's limiting. The O2 is limiting. Okay, so when it says what is the limiting reactant, it's the oxygen, okay, the O2. Now, the excess reactant is the other guy. Okay, so C2H4 is excess. That means you're going to have some of that left over. So, what is the limiting reactant? So I just said that. You write it down here. How much of the non-limiting reactant is in excess? So what you do is you simply take the bigger of these 2 numbers and subtract the smaller. So 0.21 minus 0.93. So show the work here. Okay, show the work here. 0.21 minus 0.93 equals whatever that equals. And you do that on your calculator. And that's how much of the C2H4 you have left over. Okay, now the reaction that's going to run is the one that has 2 yeses in it. So now we're going this way. And the one that's going to actually run is this one because it has 2 yeses. Okay, we can use up all of the O2, and we won't have used up all of the C2H4, so we won't run out of C2H4. This one does not run. If we try to combust all of the C2H4, we're going to run out of O2 because we don't have that much. So I'm going to put a line through that one. So you do not need to enter anything in these boxes. Okay, this top reaction is irrelevant. Okay, so that's what you're going to write. So how many moles of CO2 and H2O? Well, it's just a relationship here. Okay, you have a 1 here. This is the reaction we're interested in. You have a 1 here and a 2 here. So this number is simply going to be twice this number. Again, it's just a 2-to-1 relationship, okay? Very easy. And that's going to be 0.18 or 19. Either way is fine, okay? 0.18, okay? In other words, if this is twice this number, then this has to be twice this number. Remember, these aren't specific numbers of moles. They're relationships of how many moles you have of one reactant or product for how many moles of another one, okay? Now, since these 2 coefficients are the same, then this number has to be the same as this one, and that's 0.18, okay? So you're going to write that down here for letter D, okay? And then how many grams of CO2 and H2O are produced? So you're going to start with the number of moles. Let's start with CO2. Okay, so we have 0.18 Again, I'm coming from this point right here, up there. And that's how many moles of CO2 we got. So we get 0.18. Then you have to use the molar mass of CO2, and you're trying to go in the grams direction, so grams goes on top. And that gives us 7.9 grams of CO2 would come out of this reaction. Okay, for H2O, the same thing. It's again 0.18. They both happen to be the same. It's not always are they going to be the same. Let me get on screen here. And the molar mass of H2O is right there, 18.02. And that's going to give you 3.2 grams of H2O. I'm not concerned too much about significant figures at this point. Okay, so that's your final answer for question 24.